In this video, we are going to cover most of what we need to know about 5G SSB Synchronization Signal Block. Let's have a look into the following mind mapping figure, which covers most of the related information about SSB. 1. SSB main functions. 2. SSB frequency location identification methods. 3. Frequency domain resource allocation. 4. Time domain resource allocation. 5. SSB beam scanning. 6. Relations with other channels and reference signals. 7. SSB overhead calculation. 8. Main parameters. This section introduces SSB meaning and functionality and will cover and simulate the cell search procedure, including how UE scans and detect SSB. SSB stands for Synchronization Signal Block and is used during cell search and mobility. It consists of PSS, SSS, and PBCH. It occupies 20 RBs and 4 symbols. Now, let's have a look and insight for the cell search procedure and to visualize the overall procedure of synchronization and initial access. Once the UE power is turned on, UE will start scanning the band to find SSB frequency location. The right-hand figure will simulate how the UE will scan the band until detecting SSB frequency location. UE start frequency scanning FRM the bottom of the band. The above-mentioned two assumptions are being used in this simulation example. 1. Assuming SSB configured at mid of the band. 2. Assuming N77 band used, 100 MHz. After the UE detected SSB location, it will start decoding PSS primary synchronization signal, then SSS secondary synchronization signals in sequence to acquire and obtain the PCI primary cell ID. Then the UE will decode PBCH physical broadcast channel to obtain and retrieve MIB master information block and SIB1 system information block type 1 information which is needed to complete the initial access. Lastly, after the downlink synchronization has been completed, the UE will start PRACH physical random access channel procedure to complete the uplink synchronization. The main question that might come to your mind is, how do we configure the SSB frequency position? Generally, two main ways are used to configure the SSB frequency position. 1. ARFCN, which stands for Absolute Radio Frequency Channel Number. It is delivered in the RRC reconfiguration message to inform the UE about the center frequency of SSB block directly. Mainly used in 5G NSA and handovers. 2. GSCN, which stands for Global Synchronization Channel Number. It used to define a set of allowed center frequencies for the SSB block. It can be used in 5G non-standalone and standalone. The following sections will cover the calculation details and the main differences between both methods. We have added an Excel file and related links in the video description, which can be used to calculate related SSB frequency methods in your network. This section will present the first method used to calculate SSB frequency position from the network side. ARFCN is used to calculate center channel bandwidth and absolute SSB frequency and is called channel raster. It is used only in 5G NSA. The channel raster has a relatively high resolution using low-frequency scan granularity, 15, 30, 60 and 100 kHz. The absolute radio frequency number is delivered in the RRC reconfiguration message, which means that the UE will receive the SSB frequency domain position directly from the 4G leg. ARFCN calculation uses the below standardized 3GPP table and formula. 3GPP has defined the calculation in 3 sections to allow higher raster spacing for the higher operating bands. Now let's apply the above given formula in one example, assuming the following. The center frequency proposed is 2530 MHz, which falls in the first category, which means that delta F global and FREF offset equals 0. In this case, NRARFCN will be equal to 506,000. Now let's look at the signaling overview, which illustrates where the absolute frequency for SSB will be delivered. As shown, the signaling flow shows that UE received SSB frequency through the RRC reconfiguration message from 4GBTS. Now, let us discuss method 2, which is commonly used in 5G NSA networks and is a must for 5G SA networks. GSCN stands for Global Synchronization Channel Number, can be used in both 5G NSA and 5G SA, and is known as a synchronization raster. The synchronization raster defined a set of allowed center frequencies for the synchronization signal/physical broadcast channel block. The synchronization raster has a relatively low resolution, 1.2, 1.44 and 17.27 MHz, to reduce the number of positions a UE must check when completing a band scan. Example: the band scan procedure becomes faster and more efficient. GSCN calculation uses the below standardized 3GPP table. 3GPP has defined the calculation in 3 sections to allow higher raster spacing for the higher operating bands. The GSCN is equivalent to NRARFCN used by channel raster and is also defined in 3 sections to increase spacing between raster entries to shorten the initial access time for higher operating bands. In 5G standalone, the UE is not receiving any prior information regarding the SSB frequency position. Accordingly, the UE needs to blindly scan the complete bandwidth until locating the SSB frequency position. The band scan using GSCN was simulated at the beginning of this video. We have added an Excel file and related links in the video description, which can be used to calculate related SSB frequency methods in your network. This section will cover the details regarding frequency domain resource allocation. What exactly does it mean by frequency resource allocation in SSB? Well, after the UE blindly detect SSB during the initial access, still frequency resource location is not known to the UE. Accordingly, additional information will be delivered to the UE to be able to find and specify SS/PBCH block frequency domain position within the channel bandwidth. In general, there are 2 methods to identify the frequency domain position of the UE during 5G standalone and non-standalone. During standalone, 2 information elements will be broadcasted in System Information Block Type 1 and Master Information Block. 1. Offset to point A. Offset to point A defines a resource block offset between Common Resource Block 0 and Common Resource Block, which overlaps with the start of the SSB. 2. KSSB, which refers to subcarrier offset. KSSB defines a subcarrier offset from subcarrier 0 of the Common Resource Block identified by offset to point A to the subcarrier 0 of SSB. During non-standalone, 2 information elements will be delivered in dedicated signaling. Absolute frequency point A, it defined the position of absolute frequency of the reference resource block, Common Resource Block 0, and it represents the lowest subcarrier is known as point A, which represents the frequency location of point A and is expressed as an ARFCN. Absolute frequency SSB, it defines the position of subcarrier 0 of resource block 10 of the SS block, which can be expressed in either ARFCN or GSCN. Now let's go through the frequency offset approach /method 1 illustration. After UE completes the band scan and identified SSB frequency domain, the UE still does not know the position of channel bandwidth relative to SSB. The UE will decode MIB/SIB1 to retrieve a combination of information which is KSSB and offseto point A to locate the channel bandwidth position. As will be shown below, the UE will locate the channel bandwidth location by adding KSSB subcarrier offset to offseto point A. Approach in Method 2 is mainly using Absolute Radio Frequency Channel Number, ARFCN. In ARFCN approach, the frequency domain of an SS/PBCH block within the channel bandwidth can be specified using a pair of absolute frequencies delivered in the dedicated signaling RRC reconfiguration message. One absolute frequency SSB, which locates the center frequency of SSB. 2 absolute frequency point A, which locates the position of the first resource block in the channel bandwidth. This part will introduce the time domain resource allocation for SSB. It will explain different scenarios for how the time resources are being calculated and allocated in the frame for different bands. In other words, we can say in different cases. According to 3GPP 38213H30, the first symbol indexes for candidate SS/PBCH blocks are determined according to 1. SCS of SSB blocks, 2. Frequency band, 3. Duplex mode. 3GPP introduced 3 inputs to calculate the starting symbols of each SSB beam and the number of the maximum number of SSBs in each band. 1 SSB block subcarrier spacing. 2 formula used to calculate indexes of first symbol of SSB. 3 carrier frequencies ranges, N value. SSB starting symbol. Maximum number of SSB beams. Can be calculated after applying N factor in the formula specified in the second column. The first 2 rows are for case A, which has 2 different subcarrier spacing and frequency band. 15 kHz and 30 kHz subcarrier spacing. Formula applied is 2, 8, plus 14 multiplied by N. For 15 kHz frequency less than 3 GHz, we'll use 2 N values equals 0 and 1. For 3 kHz frequency greater than 3 GHz, we'll use 4 equals 0, 1, 2, and 3. For subcarrier spacing 15 kHz and frequency less than 3 GHz, this will result in 4 SSBs where the starting symbol will be 2, 8, 16, 22, which will be distributed in the first 2 slots. While for subcarrier spacing 30 kHz and frequency greater than 3 GHz, this will result in 8 SSBs where the starting symbol will be 2, 8, 16, 22, 30, 36, 44, 50, which will be distributed in the first 4 slots. The below figure will illustrate how the SSB resources will be allocated in the time domain for case A to C. Now let's see how SSBs will be allocated in the frame for case A using 15 kHz and 30 kHz. SSB1 at symbol 2. SSB2 at symbol 8. SSB3 at symbol 16, which is equivalent to symbol 2 at the second slot. SSB4 at symbol 22, which is equivalent to symbol 8 at the second slot. The same concept will be applied for case B and C. It also deserves to highlight that the number of SSB beams supported in a cell will be indicated through a parameter called SSB position in burst, which is broadcasted through either SIB1 or dedicated message, RRC reconfiguration. Lastly, there are some notes which need to be considered. 1. 5 time domain positions, case A to case E, are specified according to the protocol. 2. TDD 2.4 band is currently using case C. 3. All SSBs will be transmitted in total 5 milliseconds, usually in the first half of the frame. This part will cover and simulate SSB beam sweeping. Beam sweeping is a new concept newly introduced in 5G where G node B can transmit a sequence of SSB beams in a different direction. Simply, GNB can transmit a sequence of SSB beams. Beam sweeping is implemented by changing the direction of each SSB transmission. Now let's go through a simple simulation to illustrate further how the SSB beams will be transmitted. Assuming 8 SSBs will be used during this simulation. During the initial acquisition, the users will scan the signal strength for all transmitted SSB beams and report the beam with the best signal strength. As can be seen here, the users measured and reported all 8 SSB's signal strength to the GNB. SSB1 has the best signal strength as it is more directed toward the user. As shown, after the user changed his location, SSB4 was reported with the strongest signal strength among all 8 beams as it is more directed toward the UE. The same observed when the users moved toward SSB beam 8. All beams are simultaneously active, but each beam is allocated a separate SS/PBCH block within the SS/PBCH burst, so each beam transmits its SS/PBCH block with different timing. This allows the UE to see the transmissions from each beam and beam indices, which clearly can be identified based on the timing of the SS/PBCH block. This section will introduce the main parameters related to SSB. 3GPP-TS 38.213 specified 3 main parameters that can be tuned for SSBs and are being transmitted through SIB1 or dedicated signaling, RRC reconfiguration message. First parameter is the SSB periodicity. SSB periodicity specifies the periodicity of SSB burst. In other words, it controls the number of times the SSB blocks will be transmitted in the time domain. It mainly has 6 values which 5, 10, 20, 40, 80, and 160 milliseconds. Second parameter is the SSPBCH block power. Indicates the power of a single resource element used by SSS/PBCH/DMRS. It can be tuned in case if you need to increase SSB coverage footprint. It has values ranging from -60 to 50 dBm. The third information is the SSB position in burst. The in1 group bit string information indicates which SS/PBCH blocks within a group are active. The information values will vary depending on SCS and band used. Here we are showing 2 examples covering different scenarios. Example 1, 111100 means only 4 SSBs are transmitted. Example 2, 111111 means 8 SSBs are transmitted. Below is an example from Layer 3 messages, SIB1 information, covering all the above-mentioned parameters. Now let us simulate 2 different sets of combinations for SSB periodicity and SSB position in burst in the time domain. Example 1 will assume SSB periodicity 20 milliseconds. SSB position in burst 1111000 means 4 SSBs are active. 4 SSBs blocks will be transmitted at the first 5 milliseconds. Then the new SSB broadcasting will be after 20 milliseconds, which presented here at the 3rd and 5th frame. Example 2 will simulate SSB periodicity 10 milliseconds. SSB position in BERT 11111111, 8 SSBs are active. Since the periodicity is 10 milliseconds, this means all SSB's blocks will be transmitted in the first 5 milliseconds at each frame. In this section, we will introduce SSB overhead calculation. The overhead consumed by SSB will vary with different bandwidths and SCS configurations. The following are the main factors involved in SSB overhead calculation. 1. The sum of the number of PSS, SSS, and PBCH resource elements, which is fixed values. 2. Number of SSBs in a frame, which change based on configuration. 3. Total resource blocks, variables, total number of slots per frame, variables. 4. Total number of symbols, which is fixed values. In more simple words, you need to calculate the total number of resource elements being used by SSBs in a frame and then divide it by the total available resources in the frame. Let's have a look at the formula suggested calculating SSB overhead %. SSB overhead % equal to primary synchronization signals resource elements plus secondary synchronization signals resource elements plus PBCHREs. Then multiply the results by number of SSBs in frame. Then divide the results by total resource blocks available in the band. Then multiply by 12 subcarrier. Then multiplied by number of slots per frame. Then multiplied by the number of symbols. Now assume 1. Bandwidth equals 40 MHz. 2. SCS equals 30 kHz. 3. Number of SSB beams equals 8. After applying all these assumptions to the formula, this will result in a 1.94% overhead.
What main concerns and recommendations need to be considered when configuring the SSB frequency position?
It is recommended to configure the SSB frequency domain position at the bottom/start of the band, especially in 5G standalone, to reduce the cell search time and, accordingly, will improve the access delay. In case you have different bandwidth configurations operating under the same frequency band, ensure configuring the SSB at the exact location for all sites, as this will reduce the unnecessary inter-frequency handovers and will also mitigate the interference caused by SSB from and to PDSCH. Example, N78 operating with 80 MHz at Site A and with 60 MHz at Site B.
What are the differences between NSA and SA-SSB frequency domain position identification? And why 5GSA is using only GSCN during SSB scan?
In NSA, the UE will receive SSB frequency domain position through the RRC reconfiguration message, which is very useful as it will make the UE find SSB position very fast compared with 5GSA. Also, the power consumption will be less as the UE doesn't need to scan the entire bandwidth to find SSB position. Channel raster RFCN uses low granularity, 50, 60, and 100 kHz. In SA mode, SSB follows GSCN rasters. Raster means that there are some unique locations, and SSB follows some particular location every time, which means the UE should scan these locations using certain granularity which differs from one band to another, 1.2, 1.44 and 17.4 MHz. In 5GSA, it is not recommended for the UE to scan the band with the same granularity used in 5G NSA, as this will also increase the initial access time and power consumption.
How does the UE demodulate the PBCH reference signal and measure RSRP?
The UE uses DMRS, demodulation reference signal, to determine the impact of the propagation channel. The UE can also use the SS as an additional demodulation reference signal due to its location within the PBCH. Example, the propagation channel experienced by the SSS will be like the propagation channel experienced by the PBCH, and the DMRS occupies 25% of resource element allocated to the PBCH.
I am still confused about the several parameters introduced earlier in this video, such offset point/KSSB and absolute frequency SSB/absolute frequency off point A.
Let me clarify further in 3 points. 1. Simply, all these parameters are mainly delivered to the UE to guide the UE about the SSB position in the channel bandwidth. 2. Offset point A/KSSB are delivered in 5GSA, and absolute frequency SSB/absolute frequency off point A are delivered in 5G NSA. 3. These parameters are not user configured, as they will be identified by the BTS after configuring the SSB frequency domain position.
What are the main advantages and disadvantages of beam SSB beam sweeping?
In general, transmitting SSB beams in a different direction is part of beamforming, which is expected to offer a gain in coverage and interference, SI/NR. However, more beams will introduce an extra overhead for the resources occupied by SSB and for the resources occupied by CoreSet, SIB1, as each SSB beam will be associated with SIB1.